How do you solve a huge medical problem? Well, you might think the answer is always in biology. But what if I told you that sometimes the key is actually in chemistry, in these tiny invisible forces that hold our world together? Today, we're diving into the incredible story of a brilliant chemist who used that exact knowledge to tackle a truly devastating disease.
Centuries, leprosy wasn't just a terrible illness. It was a social death sentence. People who had it were often completely ostracized, forced to live apart from everyone they knew and loved. So, finding a real, effective treatment wasn't just a medical goal, it was a deeply human one. The stakes were incredibly high.
And by the early 20th century, there was this little glimmer of hope, an oil that came from the chalmoger tree. It really seemed to have some medicinal properties that could fight the disease. But, and this is a big but, it had a massive flaw, a problem so big it made the oil almost useless.
So here's the deal. The oil was unbelievably thick and sticky. It was so thick that trying to use it was not only incredibly painful for patients, but it was also just ineffective. It couldn't get absorbed by the body the right way. So you had this potential cure trapped inside this unusable goo. To unlock it, someone had to figure out the chemistry. They had to answer one simple question. Why was this oil so thick?
So what exactly made this stuff so hard to work with? Well, the answer comes down to a property we actually see all the time in our everyday lives. It's a little something called viscosity.
Think about it. Why does honey ooze out of the bottle so slowly while water just splashes right out? Or why is motor oil so much thicker and goopier than, say, gasoline? This is the exact same question that needed an answer to solve the problem with chalmogura oil.
Honey and motor oil are pretty much the perfect way to think about this. They both have a really high resistance to flow. And chalmogura oil was playing by the same rules. It was just too sluggish, too thick to be used as a medicine.
Now, the sciencey term for this, of course, is viscosity. It's just a measure of how much a liquid fights against flowing. So a high-viscosity liquid has a ton of internal friction holding it back. The mission, then, was to figure out how to dial that viscosity way, way down.
And here's where it gets really cool. The cause of this very visible problem, the thick, slow-moving oil, is something completely invisible. It's all happening on a microscopic scale, down at the level of the oil's individual molecules and the tiny forces acting between them. So to figure out how to change the oil, first we've got to understand these forces. You can almost think of them as a kind of molecular glue that holds the whole liquid together. Some glues are weak and easy to pull apart, and some are just super, super strong. The technical name for this glue is intermolecular forces, or IMFs for short. Now, it's really important to know, these aren't the bonds holding a single molecule together. These are the forces of attraction between separate neighboring molecules. And these forces are everything. They decide if something's a solid, a liquid, or a gas, and they are the absolute key to controlling viscosity. Okay, so the most basic type of this molecular glue is called the dispersion force, and every single molecule has it. See, electrons are constantly whizzing around, and just by chance they can kind of pile up on one side of a molecule for a split second. This creates a temporary negative charge on that side and a temporary positive charge on the other.
That little flicker of charge in one molecule actually causes a ripple effect in the molecule next to it. For just a fraction of a second, the positive side of one molecule is attracted to the negative side of its neighbor. Now, it's a pretty weak and temporary force, but when you have literally billions and billions of molecules all doing this, it starts to add up.
But what if a molecule isn't just temporarily lopsided? What if it's permanently polar? With one end that's always a little bit positive and another that's always a little bit negative. Well, that creates a much stronger and more reliable attraction. We call that a dipole-dipole force.
The best way to picture this is to think of them like tiny little magnets. The positive end of one molecule is naturally drawn to the negative end of another. This makes them all line up and stick to each other way more tightly than molecules that only have those weaker dispersion forces. And that stickiness is what creates higher viscosity. So, let's recap. We've got this super thick, viscous oil. And we know it's because its molecules are being held together really tightly by these intermolecular forces. This was a seriously complex chemical problem, and it was going to take a truly brilliant mind to figure it out.
And that brilliant mind belonged to Alice Ball. She was a young, incredibly talented chemist at the University of Hawaii. And get this, she was only 23 years old when doctors who were just desperate for a solution came to her. They needed someone who really, truly understood the chemistry of this oil.
Her challenge was so specific and so difficult. She had to find a way to chemically break up that molecular glue, to weaken the intermolecular forces just enough so the oil could flow freely and be used as an effective injection. But, and this is key, she had to do all of that without destroying the active compounds in the oil that actually fought the disease. A real tightrope walk.
So how on earth did she do it? It's not like she could just dilute it with water or something. No, she had to go in and fundamentally change the oil's recipe at the molecular level.
And her process became famously known as the Ball method. It was this elegant multi-step chemical procedure. Through a series of careful steps involving acidification and purification, she was able to isolate the oil's active ingredients. Then, she chemically modified them into something called ethyl esters. Basically, she gave the molecules a makeover, changing their shape and properties so they wouldn't stick to each other nearly as much.
And the result? I mean, it was a total game changer, night and day. Before Alice Ball, you had this thick, unusable sludge held together by strong intermolecular forces. After her work, you had a free-flowing liquid, a real medical treatment, all because she had cleverly weakened those IMFs. She turned a painful problem into a life-saving solution.
And, to really appreciate just how brilliant her solution was, it helps to know about the whole range of these forces. For example, there's the superstar of IMFs, the hydrogen bond. It's an extra strong type of attraction that gives water all of its weird and wonderful properties. Alice Ball's genius was that she understood this entire molecular toolkit so well that she could target and weaken these specific forces in the oil without messing up the whole thing.
What Alice Ball did wasn't just some neat experiment in a lab. It had a real, profound, and lasting impact on tens of thousands of people's lives.
For over 20 years, until new drugs were developed in the 1940s, her method was the go-to effective treatment for leprosy. She created the first real solution, which meant that countless people could finally be treated, cured, and freed from a life of isolation.
Alice Ball's story is just such a powerful reminder that sometimes the biggest solutions come from understanding the smallest things. She looked at this thick, useless oil, and she saw a way to re-engineer the invisible forces between its molecules to literally save lives. It really makes you wonder, doesn't it? What other massive global problems, from creating new sustainable materials to cleaning our oceans, are just waiting for someone to find the solution hidden in that molecular glue?